Okay, so for today's lecture, we are going to continue discussing alpha alkylation. And in our first lecture, we talked about the fact that there are three methods to alpha alkylation, specifically to introduce stereochemistry. In sophomore organic chemistry, we only talk about the reaction. We don't talk about how you form a racemic mixture, which is really inefficient. And so in this case, we're talking about how to form one enantiomer over the other. And we talked about David Evans' oxazolidinones. And so what I'd like to do in this lecture is talk about method number 2. Which is Andy Meyer's pseudoephedrins. And Andy Myers first discovered this in 1997 at Caltech. So down in Southern California, he's now at Harvard. One of his first publications was a JACS publication. And if you remember from last week, JACS just stands for Journal of American Chemical Society. Just a quick reminder. It's a 1997 paper. It's a really beautiful and thorough paper. And he specifically uses these natural substances known as pseudoephedrins. And I'm sure you've all heard of these before. They're, again, natural substances. They're found in shrubs known as ephedra, and they're used to relieve nasal and sinus congestion. And so if you've ever used Sudafed, right? If you've ever bought Sudafed to relieve nasal and sinus congestion, you're taking pseudoephedrins. Okay, so it's pretty cheap. Clearly, it's commercially available. It's a natural substance. And there are two forms of these pseudoephedrins that I want to talk about. And let me draw them out for you. The first one is known as RR pseudoephedrine. Not surprisingly, the RR is for the stereochemistry. There's only two stereocenters in this natural product. And the second form is the enantiomer. Which is SS pseudoephedrine. So just like with oxazolidinones, you've got your chiral organic molecule and its enantiomer. They're cheap, commercially available. Why are these better than Evans oxazolidinones? So why are pseudoephedrins better than Evans oxazolidinones? And I'm going to go ahead and highlight this. And so if you remember from last week's lecture, Evans oxazolidinones were limited with the type of alkyl halides you could use. For these pseudoephedrins, oh, excuse me. You can use a wide variety of alkyl halides. Specifically, you can have beta branched alkyl halides. Remember from last week's lecture, I told you, despite the fact that this is a primary alkyl halide, it is beta branched. And because it's beta branched, it gives a low yielding reaction if you use Evans oxazolidinones. With Andy Meyer's chemistry, your yields are anywhere between 90 and 99% using beta branch systems. So yields are greater than 90%, and your diastereoselective ratios are greater than 99 to 1, which is pretty neat. You're not limited to the type of alkyl halides you can use for pseudoephedrins. Okay. And if also you remember at the very end of last week's lecture, I said Evans oxazolidinones are typically used to begin a total synthesis. It doesn't mean that you can't use Andy Meyer's to start a synthesis. I think most synthetic chemists want to highlight both methodologies, and so they start with Evans oxazolidinones and they finish it up with Andy Meyer's. Again, you can start with Andy Meyer's chemistry. You're not limited to starting with Evans. It's just nice to highlight both methodologies. And then finally, one of the pros of using pseudoephedrins over Evans oxazolidinones is that you don't need acid halides to introduce and couple pseudoephedrins. So with Evans oxazolidinones, when you coupled the oxazolidinone to the carbonyl compound, you had to start with your acid halide, right? You had to convert your aldehyde, your alcohol, your alkyl halide to an acid halide. Pseudoephedrins, you don't have to start with acid halides. You can start with an ester. You can start with an acid anhydride or an acid halide. You're not limited to acid halides alone. Okay. And we'll get into that in a couple of seconds. And what I'll do is I'll introduce the methodology just like I introduced Evans oxazolidinones in 4 parts. So how does this work? And part 1. Ooh. Couple your pseudoephedrine and your carbonyl compound. Just like we did with Evans oxazolidinones. So let me introduce the following. Pseudoephedrine, oh, excuse me, this is supposed to be a methyl group. And just like I mentioned before, you can use an acid halide to introduce your carbonyl compound onto your pseudoephedrine, but you're not limited to an acid halide. You can also use an ester. I'll use a methyl ester. You can also use an anhydride. Where if you notice, they all bear the same carbonyl compound you're trying to introduce. The only difference is, of course, the leaving group, right? And this you learned from Chem 124. These are all carboxylic acid derivatives. The only difference between them is, of course, the leaving group. These are all great leaving groups. Just like before, you need a base. And you introduce and couple the pseudoephedrine to your carbonyl compound of choice. So very similar to what we saw with Evans oxazolidinones. Oh, excuse me. I wanted to highlight this yellow. Okay. That's it. That's all there is to it. Very similar to what we'd seen before. Step 2 is forming the enolate, just like with Evans oxazolidinones. Now things slowly start to change in this case, and I'll tell you why in a second. It'll become a little bit more obvious. I'll take the molecule I just made. So this is forming your enolate. And let me title this as well. Form enolate. And I highlighted this yellow in my previous step. Just with like Evans oxazolidinones, you treat this with LDA at minus 78 degrees Celsius. It's a really strong base if you don't remember from last week's lecture. It's a strong base. It's a negatively charged base. Now, in this case, what ends up happening is you're going to have to add an excess of lithium chloride. And we'll discuss this in a second. Must have an excess of lithium chloride. And not surprisingly, you are going to not only form your enolate, but because LDA is such a strong base, it also ends up deprotonating that alcohol you've got. Okay. So LDA deprotonates not only your alpha hydrogens, which are acidic, but it also deprotonates your alcohols, which you learned in Chem 24 and 124 that alcohols are acidic as well, right? They're proton sources. And so you've got your strong base, it deprotonates, and it deprotonates both the oxygens and the alpha hydrogens. I'll get to what's going on in a second. Let me just tell you that the first thing that you should note is that you will always form the Z-enolate, just like you did with oxazolidinones. If you remember, all we did was you cut the molecule in half. You note the priority of each substituent. They're on the same phase. You form the Z-enolate over the E-enolate because the E-enolate is sterically hindered. I just want to dry it out to sort of drive my message home. Sorry, starting to draw the enantiomer. So this is the E-enolate. And just with like David Evans oxazolidinones, you've got sterics, right? You don't want those sterics, so the E-enolate isn't favored. It's the Z-enolate that's favored, okay? Same thought process as with Evans oxazolidinones. That's not new. What is new in this case is the excess lithium chloride, and that's what I want to discuss now. So when you've got LDA, the LDA goes after the alpha hydrogen and the alcohol. And so because it's got two things to go after, it doesn't finish deprotonating the alpha hydrogen. Okay? And so what ends up happening is you need that excess lithium chloride to counterbalance anything that you've made. You need to counterbalance any conjugate base that you've made. The LDA alone can't counterbalance everything you've made. And what they found is that without lithium chloride, it results in the oxygen also getting alkylated. Which makes sense, right? Your O minus now becomes a nucleophile and it also wants to get alkylated as well, not just your alpha carbon. And so the lithium chloride, that excess lithium chloride, is there to not only counterbalance your oxygen, but they think something is happening where it's forming a chelate. So what do I mean by that? So take home message, you need lithium chloride and you need an excess of it because without it, it's going to alkylate the oxygen as well. So what's happening? And that brings us to step 3. And step 3 says alpha alkylation of the Z-enolate. And what I'm going to do is just going to redraw the product I made. And this is when, hopefully, I'll try to draw it as best as I possibly can. You are going to have to see things three-dimensionally and rotate things around in your head. Okay? So I'm going to redraw this molecule. And I'm going to redraw it down here. And what I'm going to do is I am going to rotate around this single bond where my methyl group is going to take the position of where the enolate is, and the enolate is going to take up the position of the methyl group. Okay, so we'll draw it out slowly so that you can see what's happening. And so the first thing that I'll do is I'll draw the methyl group where the enolate was once before. And then I'll go ahead and draw the enolate down at the bottom. Okay. Okay. And so what they think is happening is that this excess lithium chloride and the LDA are actually forming what's known as a chelate. And they're doing that where one of the lithiums is bonded to the oxygen, both oxygens, and the other lithium is also bonded to the oxygen. And it's forming a 4-membered ring chelate. And chelate is just a fancy word for organic molecule ionic bonding to a metal. So you can see that four-membered ring. And it's the organic, the oxygen's binding to the two lithiums. One lithium is from your LDA, and the other lithium is from your excess lithium chloride. Now, this four-membered ring actually is the reason why the oxygen doesn't get alkylated, okay? Responsible for oxygen not getting alkylated, which makes sense. It's too busy forming a four-membered ring that it can't get alkylated. And so you need that excess lithium chloride to form this four-membered ring so it doesn't get alkylated. And so now that I've got this four-membered ring going on, I can introduce my alkyl halide. Now, how is this alkyl halide introduced? Where is it coming from? The first thing that you should worry about is this methyl group. This methyl group is coming from the back. So this specific methyl group is blocking the back, which means that my alkyl halide has to come in from the front. Must come in from the front. So just like with your oxazolidinones, if I redraw this and I have my alkyl group come in from the front, I'm going to call this R prime. All I've got is my R prime is now wedged. And it's wedged and opposite to my methyl group. Okay? Now, all I'm going to do now is I'm going to redraw this. And I'm going to redraw this so that my methyl group is now facing down and my carbonyl group is now back to where we started. And if I redraw it and I rotate things around again, my R prime group is now dashed. And this is known as the syn product. So this is where things start getting pretty tedious trying to understand the stereochemistry, because it makes sense, right? The methyl group is blocking the back. The R prime group, the alkyl group, has to come in from the front. Makes absolute sense. It's when you start rotating things to get things back to how we started, now it's dashed, which makes sense because if you're rotating this 180 degrees to get it back on the plane of the page and to the right, then it has to flip over from wedge to dash. There's no chemistry occurring. These are the same two compounds. These two compounds are exactly the same. They're equal to each other. I'm just rotating. All I've been doing as I've been showing you things, is rotating things around. Okay. So this specific pseudoephedrine, and this is your SS pseudoephedrine, where the methyl group is dash, will always give you the new R group dash as well. And the reason for that is because of the four-membered ring chelate that you make. Okay. Not surprisingly, if you use your R enantiomer, let me draw that out for you. Sorry, let me draw out the enolate instead. So we're consistent. You are going to get the syn product as well. Where your new R prime group is wedged. So notice that the methyl group and the R prime group are syn, just like they are in this case, syn. Okay. Now, this is probably one of the harder concepts to understand because there is so much rotating around in order to get your final product. Okay. If you're not able to see the rotating and why this started off as wedged and now is dash, you should come see me. You really need to see this three-dimensionally in order to understand it. Okay. Okay. So this is for introducing your alkyl group at the alpha position. Please notice that once you introduce your alkyl group, you still have an O lithium. You just do a quick workup of acid as you typically do when you form Grignards, excuse me, or alkyl lithiums, and you protonate your oxygen. Right? And you no longer have a salt. You no longer have an O lithium. Okay. So this is all a reaction. And then, of course, your workup. If you've all done research, which you all seem to be doing research, you know that you just work it up and then you protonate and you can get your organic molecule back out. So that's step 3, alkylation of your enolate. Step 4, which is the final step, just like with David Evans oxazolidinones, is removing your pseudoephedrines. Now, very similar to oxazolidinones, actually, they're a little bit more efficient for pseudoephedrines. The reactions are a little bit more efficient for pseudoephedrines, and you'll see why in a second. Okay. You can run a hydrolysis with sulfuric acid and water to form your carboxylic acid. So this is just hydrolysis conditions. Similar to what you learned in Chem 124. You can also reduce these to primary alcohols. These do require a very different reducing agent. These are typically, this reducing agent is a borohydride reducing agent. It's not lithium aluminum hydride. This borohydride reagent is specifically used reducing agent and commonly used for amides. Okay. You can also reduce them to aldehydes by using following reducing agent. Actually, let me move it a little bit so that you can see the whole thing. And so if you notice, it's not just your typical lithium aluminum hydride, right? This is lithium aluminum hydride reagent with ethoxy groups, and these bulky groups make it less reactive than lithium aluminum hydride. It doesn't reduce esters, it doesn't reduce carboxylic acids, so it's not as reactive as lithium aluminum hydride. Not as reactive as lithium aluminum hydride. So it doesn't work with everything. It only works with amides, and it reduces them to aldehydes, which is really nice. And it's got these bulky groups that it can only reduce once. And then finally, you can also use Grignard reagents or alkylithium reagents and form ketones. So, Dr. Lucero, why can we form ketones with this? If you remember, in the Evans oxazolidinone lecture, we had to go through a Weinreb amide. We needed to go through a Weinreb amide. We needed to go through a 5-membered chelate, right? Luckily for us, despite the fact that this isn't a Weinreb amide, there's an oxygen there that can chelate and can form a ring with our Grignard or our alkylithium, and it avoids the addition of the Grignard and the alkylithium adding twice to form a tertiary alcohol. So instead, it only forms a ketone and not a tertiary alcohol, which is really nice. And I don't have to go through the Weinreb amide. The alcohol is already there, or the oxygen is already there to chelate with the magnesium or the lithium. Okay. So it makes it super nice that I can avoid a step. I don't have to form the Weinreb amide. I can go straight to my ketone from this pseudoephedrine intermediate. Okay. Okay, so what I'd like to do now is introduce a total synthesis and highlight both Evans oxazolidinones and Andy Meyer's pseudoephedrines. So the next video that I'm going to post is that of a total synthesis highlighting both, and then I'll introduce method number 3.